So, what if I told you that the secret to immortality isn't really hidden in our genes, but in the fundamental laws of physics? Today, we're going to take one of humanity's oldest obsessions and reframe it, not as a biology question, but as a pure physics problem.
And that brings us to the big question for today. Is death really our biological destiny, or is it just a physics problem that we haven't managed to solve yet? The answer, believe it or not, starts with a huge cosmic conflict that defines every single living thing.
You see, at its absolute core, the story of life is a story of conflict. It's a constant, relentless, desperate fight against the most powerful and fundamental law in the entire cosmos.
Right, and that law is the second law of thermodynamics, and its enforcer is entropy. You can think of entropy as a kind of cosmic tax. Absolutely everything in the universe, from stars down to our own bodies, has to pay it. It's the force that just wants to pull everything apart, the thing that causes decay and disorder. So life really is this heroic and usually temporary act of rebellion against this one-way street to chaos.
So this really is the core question we're tackling. Is it possible that aging and death aren't inevitable parts of our design? That maybe they're just a massive prediction error that our system fails to correct? This one idea, if it's true, could reframe everything we think we know about being alive. But this is where it gets really interesting. It brings us to a paradox, something the physicist Erwin Schrödinger pointed out way back in 1944. Unlike a cup of coffee that always inevitably gets cold and becomes one with the room, living things do the exact opposite. They create and maintain this incredible, complex order in a universe that is just screaming for chaos. So, how on earth do they do it? Well, it turns out life is sneaky. It found a loophole, a kind of survival algorithm that allows it, at least temporarily, to win its fight against the cosmic tide of chaos.
And this is where the theoretical neuroscientist Karl Friston comes into the picture. His idea, the free energy principle, totally reframes survival. He argues it's not really a biological process at its core, it's an information problem. You see, to stay alive, an organism has to stay within this very, very narrow set of conditions. The right temperature, the right blood pressure, you name it. Any deviation from that perfect state, well, that's a surprise. And to live is simply to minimize that surprise over time.
Okay, so how do you actually minimize surprise? Well, life has two main strategies. The first is what's called perceptual inference. Basically, you change your mind. You see what you think is a snake, you get a closer look, and you realize, oh, it's just a rope. You've updated your internal model to match reality. But the second one is even more important, active inference. This is where you change the world. You don't just accept that you're cold, you actively put on a coat to make the world match your expectation of being warm. This constant dance between the two is really the essence of staying alive.
Now, for any of this to work, for there to even be a you to minimize surprise for, there has to be a boundary, a line in the sand separating you from the rest of the universe. In physics, this has a really cool name, a Markov Blanket. Just think of it as your personal shield. It's your skin, your senses, your muscles, everything that lets you sense the world and act on it, without just dissolving back into the cosmic soup.
Okay, so this all sounds pretty theoretical, right? What does this actually look like in practice? Well, meet Bryan Johnson. You might have heard of him. He's often called a biohacker, but honestly, it's way more accurate to see him as the first human to systematically try to turn his own body into a high-fidelity active inference machine.
And his goal is brutally simple and incredibly powerful. It's not about wellness or feeling good, it's just don't die. Now, this isn't just some edgy mantra. In the language of this theory, it's what's known as a hyperprior. It's the single, overriding goal that organizes every other action and belief in the entire system. It is the ultimate instruction to minimize surprise. And here's exactly how he does it. His system, Project Blueprint, is a perfect cybernetic loop. First, high-fidelity sensing. He measures over 70 of his organs using everything from ultrasounds to MRIs to constant blood panels to get a crystal-clear picture of his internal state. Second, his model of what's good for him isn't based on his feelings, but on massive, population-level scientific studies. Third, active correction. He takes over 100 supplements and follows a super strict diet to correct any deviation, any surprise his sensors detect. And finally, and this is crucial, he automates everything to subdue what he calls the rascal, that impulsive part of our brain that craves things like donuts and staying up late, the very things that increase our long-term decay, our entropy.
So, does it actually work? Well, the data is pretty wild. While a normal 45-year-old ages 1 biological year for every chronological year, Johnson's rate is just 0.69. His cardiovascular fitness is in the top 1.5% of 18-year-olds. He is actively, measurably slowing his body's march towards entropy.
And maybe the most stunning number of all is this one. His project has achieved a 5.1-year epigenetic age reversal. He hasn't just slowed down a key marker of aging, he's actually reversed it. This is a real-world, honest-to-goodness demonstration of entropy reduction in a human being.
So if humans can run this survival algorithm, what about artificial intelligence? Surely they could do it better, right? Well, this is where we hit a massive, massive roadblock with the AI we have today.
To get this, you have to understand this crucial distinction. Most AI today, like the big language models you know, runs on what we can call immortal computation. The software is totally separate from the hardware, and this takes enormous amounts of energy for cooling and error correction because you're basically fighting against physics. But biology, it uses mortal computation. The software is the hardware. Your memories are actual physical changes in your brain, and by embracing physics instead of fighting it, life becomes incredibly efficient. The best way to think about a large language model like ChatGPT is as a brain in a jar. It has been fed a huge snapshot of the past, the internet, but it has no body. It has no Markov blanket. It can't perform active inference because it can't actually act on the world and see what happens. It's totally disconnected from physical reality, which, by the way, is exactly why it can so confidently hallucinate.
And this disconnection leads to a gigantic problem. They are unbelievably inefficient. Your brain runs on about 20 watts of power. That's the same as a dim light bulb. Training a big AI model, that takes megawatts of power. From a purely thermodynamic perspective, they are completely unsustainable. They produce a massive amount of entropy, of heat, just to generate information. They are fighting physics, and they are losing. Badly.
But a new kind of AI is starting to emerge, one that is built from the ground up on the very same principles that govern life itself.
And the difference is just staggering. Check out this benchmark. On the left, you have a state-of-the-art model from Google using the standard approach. On the right is Axiom, an AI built on active inference. It doesn't just perform better, which it does, it learns nearly 8 times faster.
And that efficiency, it translates into incredible performance. Axiom learns almost 8 times faster, it uses 97% less energy, and it still performs 60% better. So why? Well, it's because, like us, it isn't just finding patterns in data. It has a kind of built-in curiosity to reduce its own uncertainty and build a real model of its world, just like the free energy principle says living things do.
Okay, so let's bring all these threads together. We've seen the physics, we've seen the human experiment, and we've seen the AI. So what is the final core logic here? What's the mathematical condition for, well, indefinite survival?
It all boils down to this one simple inequality. To keep going, your system's ability to model the world, to adapt, and to repair itself, your update rate has to be faster than the rate at which entropy, which is just damage and disorder, accumulates. If you can repair faster than you break down, then in theory you don't have to break.
This really presents us with 2 completely different paths. First, you've got standard biology, which is the path we're all on now. Entropy wins. The rate of damage is faster than our rate of repair, and the result is aging and eventually death. But the second path is this radical new idea. By outsourcing our body's model to a faster learning algorithm like Johnson's blueprint or an Axiom like AI, we could theoretically make our update rate exceed our decay rate. And this could lead to something scientists call negligible senescence, a state where aging just isn't a factor anymore.
All of this points to a really profound final concept, mortal computation. And here's the paradox. For an intelligent system to have a chance at surviving indefinitely, it has to be mortal. Its software has to be totally inseparable from its physical hardware. Your brain is mortal. If the hardware dies, the software is gone. But that very fact is what makes it so incredibly, unbelievably efficient. So the future of immortality might not look like the sci-fi we imagined. It's probably not about uploading our consciousness to the cloud. Instead, it looks more like a two-front war against entropy. On one side, you have humans like Bryan Johnson, perfecting their mortal biological hardware. And on the other, you have a new generation of AI, finally embracing its own mortal, physical hardware to achieve truly efficient intelligence.
And that leaves us with one final, pretty provocative thought. If resisting death is fundamentally a computational problem, a problem of minimizing surprise and outrunning entropy, it kind of reframes our entire sense of purpose, doesn't it? It suggests that life isn't just something to be lived, but maybe it's an optimization problem to be solved. And the big question is, what exactly are we solving for?